Alright, what is going on, guys? Welcome back to a brand new math video. Today we are going to be working out an integral. Well, this is not the hardest integral. It does take a bit of work if you don't know how to use integration by parts. Basically, we're just going to be using integration by parts to solve this. This is a question that I had in an exam a couple of years ago, and I thought, you know what, let's just do a video on it just for funsies. Like, I am only doing this for the fun of it. Of course, I am not doing this for any serious reason. It is just what I do in my spare time, and I thought, let's do it. So let's define that integral that we want to find. So the integral of x multiplied by e to the power of x dx. Now this is not actually that hard to solve, again, if you know how to integrate already. So let me explain. So when we have a product, the integral of a product, then we can use this theory called integration by parts. This is this theorem. The integral of uv prime is equal to uv minus the integral of vu prime. Okay? This is our theory. And we can use this theory to find the integral. And the best way to do this is to simplify as much as possible. So the best way to find this integral would be allow u to be equal to x and v primed to be equal to e to the power of x. This way we can use integration and differentiation to find the derivatives and integrals of these parts. So v, we know that the integral of e to the x is just e to the x. Now we don't need constants yet. And of course the derivative of u in terms of x will just be 1. And now we can use this in this definition. So we can allow, changing colors for some reason, we can allow the integral of x to e to the x dx to equal uv. So we have our u and our v. So let's pop the u down as red and the v as pink. So we've got x multiplied by e to the x. And now we subtract the integral of vu prime. And we know that v is our pink, and we know v is e to the x. So we just do that, e to the x. And we multiply by the derivative of u in terms of x, which we found is 1. And we integrate in terms of now dx. Okay? And now this is actually solvable quite easily, because this is equal to x multiplied by e to the x, take away the integral of e to the x dx. And as before, we literally did the same integral. The integral of e to the x dx is equal to e to the x. But this time we need to add our plus c. So we get x multiplied by e to the x minus e to the x plus a constant of integration. And we have to state that c is some arbitrary constant that we don't know. And that's the reason why we don't have to go minus c instead, because this is the minus integral, so technically you would have to take away, let's say the integral of 1 was in there as well, you go take away x. But in this case we just have a constant which is arbitrarily defined. So now, how can we confirm this? Well, we can confirm this using the product rule. So if I allow this to equal I, then I prime of x, we should, in theory, get back x multiplied by e to the x, unless we've done something wrong. So we can take the derivative, the standard derivative that is, of this stuff on the right in terms of x. And we solve. So let's start with this product. So as before, we integrated a product. We can also differentiate a product using the quote-unquote product rule. So let's go ahead and do that. So we have e to the x plus x e to the x. Okay? And now we take away the derivative of e to the x, which is e to the x, from our statement here. We can differentiate and we get e to the x is equal to d dx of e to the x. So that just states that the derivative is also the same. And we have the derivative of constant, which is 0, because it is horizontal to the x-axis in this case. And here that means we have e to the x cancel and minus e to the x cancel, and we get x multiplied by e to the x. So this verifies that the quote-unquote integration by parts rule does work. And we can do many more examples of integrals using this, which I will do in another video.